Today we're going to understand the waves on a string. So let's say we have a string here and we just pull it up. We force we pull tension force into that string. So we will have all of this. So we already know what's the wave speed, that is going to be velocity is equals to frequency times the wavelength, and we'll still have other parts that we need to understand, like the fundamental frequency and the length of a string and its wavelength at different harmonics. So this is going to be the first harmonics. It is the pull. First harmonics is going to be the pull, the first, the first wave, and it does have antinode, and n is basically the number of loops. We have here the fundamental frequency. We have the length of a string. We can just calculate the length of a string by using this equation, and we have wavelength here. So these equations are already having derived, so we can just plug in everything. We have a numbers, so it's basically easy. So this is basically the wavelength of a string. So here, so this is what they call antinodes. So this is they call the antinodes. And we also have the so-called nodes. So these are antinodes here. Here is still antinodes. So basically, the up, the down, up, down, up, down, up, down, up, down. That's going to be the antinodes. But here is going to be the nodes, where the string is in the equilibrium position. It just basically hit it. So that's going to be the node. We call it node. And it's also the have a symbol n, which is the number of loops. So the first harmonics is in synchronized with the loops. So first harmonics meaning one loop, second harmonics meaning two loops, third harmonics meaning three loops, so and so on and so on. So that's going to be what we call first harmonics. So this here I just box it, that's going to be the loop. So this first harmonics, we have second harmonics, that means we have two loops, and so on. So I think that's it. We are ready to understand it. So let's just keep putting some things here. So the antinode here is going to be 2. So at n equals 2. And the node is going to be 3 at n equals 2. So n is basically the number of loops. Now let's solve some practice problem. Standing waves has 5 loops. How many nodes and antinodes are present? So this is going to be the first loop, second loop, third loop, fourth loop, and this is going to be the fifth loop. So in these 5 loops, how many nodes and antinodes are present? So how many antinodes? This is 1, 2, 3, 4, and 5. So we have basically 5 antinodes. So how many times have I said that basically? And now we're just going to put the equilibrium position of the string, or the original position of the string. So we have 5 nodes. I mean 5 antinodes. Okay. So we have antinodes of 5 here. And let's count the nodes, the number of nodes. So the nodes is basically antinodes plus 1. So we can see it here. So we got 1, 2, 3, 4. We have 5 here, and we also have 6. This is not 1 to 6. So that is the number of nodes. So it's going to be 6. So using the formula, we can just note that nodes is antinodes plus 1. Now, the fundamental frequency of a certain standing wave is 175 Hz. Calculate the first 4 harmonics. So we just put here how many harmonics here. 1, 2, 3, 4. So we're going to calculate the first four harmonics. So to do that, we can use this equation. F sub n is equals to n times f sub 1. Now let's calculate and as f sub 1. So f sub n and f sub 1, they are just the same. Just plug in n equals to 1. So that's the first harmonic. Now let's calculate the second harmonic. That's going to be twice the first one. So 2 times 175. So so the second harmonic, the frequency of second harmonic is going to be 350 hertz. Okay, now let's try the third harmonics. So the third harmonics is just 3 times the first harmonic. So 3 times 175. That's going to be, let's just box this. Let's highlight our answers. So this is going to be 575 hertz. So as we can see here, the frequency is increasing with the increasing harmonics. So the frequency of the fourth harmonics, that's going to be 4 times the original. So that's going to be 4 times 175. It's about 100 hertz. There you have it. Okay, so I'm gonna delete this illustration here. So let's solve some more practice problems using this occasion. Hopefully you save them. So the seventh harmonic of a standing wave is 780 Hz. What is the frequency of the fourth and ninth harmonic? So now, we can just plug in everything because we already visualize what we know. We already have a picture in our head on what's going on. So f sub n is equal to n times f sub 1. So we have the seventh harmonic, that's 780 Hz, and we're going to calculate the first harmonic first. So we can just plug in everything with that formula. So 780 divided by 7, it's going to be 101. So we just random it up. So now let's calculate the fourth harmonic. That's going to be f sub 4 is equals to 4 times f sub 1. So that's going to be 4 times 101. It's going to be 444 Hertz. So calculating the ninth harmonic is basically easy. So it's just going to be 9 times f sub 1, which is 1100. So we get, it's going to be 999 Hertz. So that's it. So the first is 444 and 999. A 2-meter string produces a standing wave with 3 loops. What is the wavelength? So to calculate the wavelength, we can use this equation. So lambda n is equal to 2L times n. So what we have here is a 2-meter string, and it does have 3 loops, which means that it also have 3 antinodes. So that's going to be 3 here. So that's going to be 2 times 2 meters divided by 3. Okay, so 2 times 2 is going to be 4 meters. Actually, okay, we just replace our 3. Okay, so that's going to be 2 times 2 divided by 3. It's around 1.3 meters. Now let's calculate the frequency if the speed of the wave is 45 meters per second. So to be clear here that the speed of a wave is a constant in value, so it doesn't change. Once you have put tension force into a string, the speed just remains constant, and it will eventually slow down due to friction. So now let's calculate the frequency. The speed of the wave is 45 meters per second. That's going to be 33.75 hertz. Now, what is the frequency and wavelength of the first harmonic? So we can just use this equation once again. So lambda 1 is equals to 2 times 2, and let's divide this by 1. So the lambda 1, so the wavelength of the first harmonic is going to be 4 meters. So it doesn't lose that much. It basically extends. So the verse, let's calculate the frequency. So 45 divided by 4. I think I'm stuck here. But let's keep it. Let's use our calculator here. No, don't write it here. It's around 11. So 11 hertz. So it's going to be 11.25 hertz. The wavelength of a standing wave with one loop is 12 meters. Find the wavelength of the reverse harmonics. Okay, my laptop just glitched on. So the wavelength of the standing wave is 12. Okay, so we have a wavelength of the standing waves that's going to be 12 meters. And let's first calculate the length of the string. So that's going to be 1. So 6 meters because we have one loop, it's going to be 12 meters. So the length of the string is 6 meters. So let's calculate the wavelength of the first 5 harmonics. So we can just use the equation once again. So we're using the equation simultaneously. So this is going to be the wavelength of the second harmonic. And let's calculate the wavelength of the third harmonic. That's going to be 2 times 6 divided by 3. So it's going to be 2 times 2 once again because 6 divided by 3 is 2. So 2 times 2 is 4. So that is the wavelength of the third harmonic. Now the fourth harmonic is going to be 2 times 6 divided by 4. Then we can reduce this into 1 half, which means that 6 divided by 2 is going to be 3. So this is the wavelength of the fourth harmonic. Now let's calculate the fifth one, so the last one. So we can see here that the increase in harmonics will reduce the wavelength, which is actually observed when we see a string that is oscillating up and down. So 6 times 12 is going to be 12. Let's just leave it like this. It's going to be 12 over 5. So let's leave it as improper fraction. So that's it. That's a wavelength of second, third, fourth, and 5. We already know the first one, that's going to be 12 meters. And we do not need to calculate it. So the wavelength of the fifth harmonic is 1.5 meters. Calculate the wavelength of the ninth harmonic. So what we can do here is just arrange the numbers into its order. So we have the wavelength of 5 and a wavelength of 9. So let's make them a number. So we have 1.5 times 2L, and we have 5 here. Now we can just cross multiply, so that 2L is equal to 1 plus 5. So now we can do here is just divide this. So 1.5 times 5 is divided by 2 is going to be 3.75 meters. So we have this. Actually, let's calculate the 9 because we already know the length. Okay, so what we have here is going to be 0.83 repeating meters. So that's the wavelength of the 9 harmonic. Now let's try the last one. The frequency of the fourth harmonic is 300 Hz and the wavelength of the second harmonic is 2.3 meters. What is the speed of the wave? So now, we can just reach out for the other number to be exact. So we have the frequency of 4 and the wavelength of 2. So we need a number that they are the same. So we need a frequency of 2 or a wavelength of 4. So let's just make the frequency 2. So to do that, we can use this equation. So the frequency 1, we're going to calculate the frequency of 1 first. So it's going to be 300 divided by 4. It's going to be around 75 Hertz. Okay, so now we do now have that. So let's calculate the frequency of 2. So that's going to be 2 times 75. So the frequency of the second harmonic is going to be 150 Hertz. So now the numbers are matched. What we can do here is use this. So velocity is equal to frequency times the wavelength. So frequency times wavelength is going to be 2.3 meters times 150 Hertz. So the velocity at second harmonic is, it's basically constant. So 345 meters per second. It's a lot speed.